All right, it's super fun circuit time. We're going to work a problem that follows this whole thing. Actually, two problems. We're going to start with, well, this diagram here is from the scribbly notes, right? So we're going to start with the time domain elements. We're going to get integral differential equations. Then we're going to Laplace transform into the frequency domain. We're going to get a proper rational function of S. We're going to do a proper or a partial fraction expansion or PFE of that rational function. And those partial fraction expressions we can inverse transform back to the time domain, right? And the partial fraction expansion is this methodology here, okay, where you take an expression and you break it up into these little pieces. You solve for the k's, and then you have something that you can you have an expression that you can inverse transform, right? That's what we're going to do. All right. And it's going to be a long problem right here. So, okay, given. So this is applying Laplace. RLC, we're going to do an RLC circuit. So given there's no energy when a switch is opened. At t equals 0. So we have this, it's a DC source, which is initially there's a switch that's closed. Okay, so this source is shorted out. It's not affecting the circuit, and that switch opens at t equals 0. Okay, but initially it's sorted out. But when it opens, its current, its constant DC current, goes through the circuit. So we have these elements, and it's just an RLC circuit. There's an inductor, a resistor, and a cap. Okay, we have C, R, and L. And for these Laplace ones, R, L, and C have to be known. Okay, then there's a signal of interest. This is similar to what we did in Chapter 8. We did it in time domain mostly, although we had some S's in there, and that's where those S's came from, this kind of theory anyway. So we have this I sub, this is I sub 0. And then we have I sub R and I sub L. Okay, so when there's no energy in these elements, when the switch is closed and the current's just running around in here, and then you open the switch at t equals 0, and the current through here runs through these guys here. And we want to know, well, for right, you know what, we could call this, okay, this one here, I think yeah, we're going to need I0. So I'd like to call this I sub C, but we need it later. We need to call it I sub 0. All right. So we're asked to find, should I write that one? Or fine. Asked to find the, well, two things, the integral differential, the time domain. Right? Integral differential means time domain. Expression v0 of t. I'm trying to make my v's look little there. Okay, we're trying to find v0 of t, and then the Laplace transform. So basically the frequency domain expression, big V0 of S. Right, we're trying to find those two things. And let's see, so there's no energy when the switch is opened. So what that means is, so no energy means V0 at 0 is 0. And because energy in a cap and an inductor are stored in voltage and in current, respectively. So if they're telling you there's no energy, then we know that this V0 is 0, 0, and the IL at 0 is 0. Yeah, I0, IR, and IL are all functions of time. V0 of t is a function of time. Just left off the little t symbol here because it gets crowded, right? We can also assume, in fact, this method only works if we assume that I, DC, R, L, and C are known constants. That is, the math that we derive for this won't work for other constant values. The equations will break. Okay, so here's what we're going to do. We're going to follow this strategy this strategy, right? So we're going to use node voltage at node A. This node here, we're going to write a node voltage equation. Then we're going to do a transform from the time domain to the frequency domain. And we're going to do some algebra, right? And we're going to apply equals CV prime, and then do some more algebra. And that's what we're going to do. All right, we can, before I go any further, it might be nice to just go slow because we're dealing with u of t in here, and let's go ahead and just make a little picture. So we can model the switch with u of t, the step function, right? So if you did that, just to be thinking about that, it would be u of t times this IDC. This is kind of like k, like there's often a k associated with u of t, right? And you could think of it that way. So this goes into node A, and then there's our RLC components in here. Right, just to think about the switch. Okay, we've got a whole bunch of rules that it would probably be good at this time to iterate. So we iterate. So we've got some time domain rules. Okay, we've got this guy, I sub r equals v sub 0 over r, right? That's Ohm's law, we got that. And we've got the current in a C is CV0 prime. We've got that rule, remember? That's just the current voltage relationship for cap. And we've got a current voltage relationship for an inductor, and we're going to need the integral form of that. There's also a derivative form of that, but we need this one. And this is a variable of substitution because the limits of integration are time as well. Anyway, we got that guy. We've got this u of t thing, which is a time domain thing. So we've got that. All right. So let's use node voltage here. So we're going to do node voltage at node A. And what are the rules for node voltage? Just to review, out is minus and in is plus, although you can flip those if you want. And we're summing I and V over R terms, right? That's just the method that we're doing. So I've got this u of t going in, right? And then I've got these three guys coming out, right? So I dc u of t, that's this current signal here. Got these u of t's we've got to deal with, which are freaky. Sometimes your stuff don't work if you don't have u of t's. So the current coming in from this source, and then you've got these three currents leaving: the resistor current, the cap current, and the inductor current. Three currents leaving. Then we apply these time domain rules right here, right? So we've got time domain rules. good review for the test is chapter 8 is similar to this, but different. So I dc u of t is or minus Ohm's law, V0 over T over R, that's this first term. Then the current in the cap, which is I0, is C V0 prime of T, CV prime. And then this current in the inductor, we use the integral, right? It's going to be 1 over L integral from 0 to T of V0 x dx plus the initial current in the cap, that's in the time definition, which is 0 because we're told that it's no energy. And okay, those sum to 0. We can transfer this to time domain now. Okay, so that easy. We can or to frequency domain. We can transform to S domain. And we've got a bunch of rules that I ran out of paper to write. That's why I always have lots and lots of paper. I might be able to squeeze them here, but I might not. So we've got these, for this problem, we've got some Laplace rules, right? We've got f of t transfers us to f of s. So u of t is 1 over s. And k little f of t is just k big F of s. And that's another rule. And then f prime of t is s big F of s minus f at 0 minus. These are all rules in tables 12.1 and 12.2. And then the integral from 0 to t of f of x dx is dividing by s. It's big S of s over s. Okay? So we can apply those rules now. So this is 1 over s. U of t becomes 1 over s applying this rule over here. And this thing here, so this may or may not freak you out, but this, so there's multiple, well, this is our variable of interest. Everything else is constant. So that this is our little f, basically. And this is our big F. Oops, shoot. Right in pen. So then this C, okay, then this guy here, that's this, well, C is just a constant, you just carry that down. And then the F prime of T is this thing here. That's, so this here, the little v is like the little f. And the derivative of that is S big V 0 S minus little v value prime, no, just little v evaluated at 0. And this was 0 because of, once again, no energy right here. That one was earlier. Okay, and that's this rule up here. And then here, that's this rule out of this operational transform out of table 12.2 point something. Don't know what it is. 12.2.6, I think it was. So we pull out the constant, and it's just little v becomes big V of s over s, and those sum to 0. Okay, so this was rule 12.2.6. This was rule 12.2.3. This was rule 12.2.1. And I think it's 12.1.2, I think. All right, so that was starting with the time domain circuit. We identify signal of interest. Well, we were asked to find this thing. So you apply your time domain rules. We use node voltage. And then this should seem pretty familiar up to here. And then now we just did this, right? So all of this work just so that we can apply these Laplace transforms here. So we're asked to so we actually have to get this big V 0 of we have to get the frequency domain expression first. Why is this even in the same problem here? Because we're not going to be able to get that. Oh, yeah, I'm sorry, I'm confusing myself. So here they're asking for the integral differential equation V0 of t. I forgot about the integral differential. I mean, most of the time, like a final answer is, we just want, generally speaking, we just want signals of time for voltage, current, stuff. Like an integral derivative, you know, doesn't really do us that much good in the end. In the end, we just want to see how is the signal, you know, what's happening over time to a voltage signal, right? And we just need, you know, V of t that can be plotted. But that's not what they're asking for. They're asking for the integral differential equation, which was this one, really. I mean, this is pretty much the answer to part A right here. This thing. And then they ask us to go to the, I'm gonna have to go read this problem again, but it'll be fine. Anyway, then they're asking us to go solve for this. I mean, we could, you can't here, you can't pull it out. I mean, I'm not really sure why this is worded like it is. But it's fine. Anyway, so just moving right along. Bear with me, we'll be fine. So we got to solve for us because, yeah. Okay, I went and looked it up. I wrote it down wrong. So they're asking for the integral differential time domain expression V0 of t and they say something like that governs the behavior of v sub t. They're not trying to say get V0 of t equals, because you can't do that here. Okay, you can only get this thing here. You can't isolate V0 of t out of this thing. You can't do it. But you can isolate big V0 of s, which we're going to do. And then the other thing they're asking you to find is find I0 of s. That's part C, or IDC of s. All right, this will make sense. More sense when I do the follow-on to this, where we go through all the partial fraction expansions and then the reverse transform, and we'll end up back to this thing here. But for now, all we got for V of t, this is like the best V of t that we can do now, is this integral differential expression. We can't isolate it down any further than that, but we can here in this frequency domain, right? So just solving this guy here for big V0 of s, it's going to be IDC over s minus, so factor out the big V0 of s out of all of this stuff. And so you're factoring out of this r term, and you're factoring out of this SC term, and this 1 over LS term. You're pulling the V0s out of all that stuff, so you end up with 1 over R plus SC plus 1 over SL equals 0. So V0 of S is IDC over S over this thing, 1 over R plus SC plus 1 over SL. And then that's an answer, but they are giving you an answer in the book that they want you to compare it with. And to get that, and there's a reason for it, there's a reason they're doing this, but if you multiply the top and the bottom by S over C, so you get this. You get V0S equals, S over C over S over C, IDC over S, 1 over R plus SC plus 1 over SL. And these S's cancel, and C goes underneath here, and then this C cancels that, and it ends up looking like this. This is IDC over C over, okay, and then rearranging this S comes inside, and you get S squared, and the C cancels. It's S squared plus S1 over RC plus 1 over LC. Just pulling this S over C term inside and rearranging this so that it's in descending. And this is the answer that's in the answer book. But the reason they made you verify this is this is familiar from chapter 8, right? This is the characteristic RLC equation, right, that we saw in chapter 6. So this is how this was derived, right? Remember, before we just introduced that equation in chapter 8 and said, go accept it, just go take differential equations and whatnot. But anyway, that's how it comes from. You could do this from scratch if you wanted, because here we're applying these rules which you could verify and derive. You have the Laplace integral definition. You could derive these. If you have nothing to do this summer, you spend all time on this. So this is the answer to B. Let's start here, B. Anyway, this is the answer to B, this thing. Okay, the solution to C, we want to know what I0 of S is. Okay, so here the trick is we're going to use this I equals CV prime, time domain rule. So in our case, the current in this guy, in our case, the notations we're using for the letters here, this is I0 of T is our cap current. There's the cap. And then the voltage across the cap for this problem is V, little v sub 0 of T prime. So, okay, now we can do a time to, we can do a Laplace time to frequency domain on this. So that means this little I of 0 of T is going to be big I times S. And why is there an S on here? Well, it comes from this here, that there's a U of T in there, and that that might bother you a little. It bothers me, to be totally honest with you. But like when they throw the U of T's in here and when they don't, is honestly bugs me a little bit. And I think it might just be because that's what it takes to make it work out. I mean, we do that in circuits. Generally speaking, we'll fiddle with the math a little to fit known circuit behavior, right? Like you're going to see that in one of the problems coming up with imaginary numbers. Like they always come in conjugate pairs because that's known circuit behavior. Anyway, this is one of those things, and it kind of bothers me a little bit. But anyway, there's an S in there. And then this thing here is the C is just a constant, and then we can apply this rule right here, but for little v. So it's going to be this v prime, v0 prime of t. We're just going to apply this transform right here. So it's little s, big V0 of s minus little v0 at 0. Once again, this is 0 because of the zero energy thing. And wait. Am I all right on this? Yeah, that's it. So this is simplifying this thing here. It's just SC V0 of S. And we can plug this into our equation for V0 of S that we've already solved for over here. So I0 of S is just plug in V0 here. It's going to be well, the C will can't. This should be bigger. Yeah, C is really big here, and it's a little BC. But anyway, it's going to be SIDC over S squared plus S1 over RC minus or plus 1 over LC. It's just the same. This stuff here, just the C cancels and the S comes over, and that's that. All right, so we started in time domain. We got an integral differential equation. We're unable to isolate V0, little v0 of t out of this thing, but this is the time domain expression that governs the voltage signal, little v, in time domain. But we can transfer this to frequency domain using various transforms. Okay, and here we had IDC U of t, and that's because of this switch. And once we have it in this algebraic form, we can isolate that to a function of just V0, big V0 in frequency domain. And then they want you to manipulate this so that you get something, you get a characteristic equation that we're going to play with later. It's the only reason of going through this extra step. And then there's this extra piece here where they're saying, they want to point out that you can come up with this current voltage relationship in the time domain and transfer that over to the frequency domain, all right, and then do a substitution. And I guess the similar logic applies, I suppose, that we introduced a step function here at least once. It seems like as long as you, oh, sorry, I'm off the page. Oh my gosh. Hope you can understand what I was talking about. Anyway, we introduced this step function here once. Seems like you need to do that at least once because these are one-sided Laplace transforms. They only apply to t greater than 0. Anyway, we introduced it again here, which is a little bit weird. But anyway, if you figure out if you have any insight into that, let me know. This is the first time I've taught this this chapter, so it's kind of a little bit. There's a few things I've got not so good. All right, hope that's helpful to you. Thanks.